These metal walls failed right now. More than 12,000 cubic feet of water, that nearly 340 cubic meters every single second, would flood this entire chamber almost instantly. It looks like a submarine, but I'm actually standing inside the turbine pit of a canal hydropower station, and honestly, being down here feels terrifying.
Right outside these steel walls, millions of liters of water is rushing through the canal with enormous force. And somehow,
Inside this seal capsule like chamber, a turbine and a generator is producing 12 megawatts of electricity. The first time I came down here, I could actually feel the vibration through the floor. The air felt heavy, and I felt a constant smell of lubrication oil, warm metal, and electrical equipment. It's loud, space is tight and hot, and surrounded by moving water from every direction. That would make this place feel unreal. Okay, this is a Kaplan turbine unit built directly into a canal system. Unlike the mountain hydropower plant that rely on huge waterfall and extremely high pressure water, this setup works in a completely different way. Low head but massive water flow. The head, basically the height difference between the waterfall through is only 4.8 meters or around 16 feet. So the minimum operating head is about 3.2 meters while the maximum head which is 6.2 meters. That may not sound impressive at first, but when enormous volumes of water flow continuously through the turbine, the power out becomes massive. And that is the beauty of canal hydropower. Low pressure and huge flow, continuous generation. At the heart of this pit is a giant Kaplan turbine runner with a diameter of 6.3 meters over 20 feet wide. Water enters through the intake structure, and as the wicket gate slowly begins to open, the flow strikes the turbine blade and start rotating the runner. So the wicket gate basically control how much water enters the turbine, and despite all this water flow, the turbine rotates at only 75 rpm. That sounds simple, but this machine is producing enormous torque. This is not about speed, it's about the force. And there's one component down here that makes this entire system possible, and if it fails, this 12 megawatt generator instantly becomes a giant useless spinning machine, the gearbox. You can actually feel the floor vibrating at 75 rpm, but the electrical grid connection needs a much faster heartbeat to stay alive. Okay, that is uh, um, that is where the engineering magic begins. Needs much higher rotation speed to efficiently produce electricity. So, between the turbine and generator, a massive gearbox is installed inside this bit. This gearbox increases the rotation speed by nearly 10 times. The turbine shaft rotates at only 75 rpm. But after passing through the gearbox, the generator speed jumps to 750 rpm, and that is the speed. That speed is not random. This is exactly what this 8-pole generator required to produce electricity at 50 hertz frequency. Let's do the math. The frequency equation for a synchronous generator is F is equal to N times P divided by 120, where F is the frequency in hertz, N is the rotation speed in RPM, and P is the number of pole. And we know the grid frequency, which is 50 hertz here. The generator has 8 poles, so N is equal to 120 into F divided by P. That comes out to be 750 RPM. So this generator needs 750 RPM to produce 50 hertz frequency. That perfectly matches the gearbox output speed, and that is why this gearbox is one of the most critical components in the entire system, and without it, stable grid frequency would be impossible. While all this happening, you are standing inside a vibrating steel chamber surrounded by rushing water, hot machinery, and the sound of gear transferring thousands of kilowatts of power. So the unit has a rated output of 12 megawatt. The generator itself is rated at 13.3 MVA, while operating current reaches nearly 700 amperes during the full load operation, and all this power is being generated inside a sealed metal chamber, only a few feet away from enormous flowing water. And honestly, that is the part that feels hardest to believe when you are stand here in person. The generator synced with the grid at around 3 megawatt, and the generator locks perfectly with the national grid frequency and voltage once synchronized. And then the operator gradually increases the load step by step until the unit reaches full generation capacity. From outside, the powerhouse looks calm, but inside this pit, you can feel every movement of a machine. Honestly, watching videos of this turbine is one thing, but standing inside this pit while the unit is operating feels completely different. Your brain constantly reminds you that thousands of tons of moving water is flowing outside these walls. You can hear it and feel it. Yet, despite the massive power, the entire system operates with incredible precision, entirely free of chaos or panic.
This setup is fascinating because simple engineering does exactly what it was designed to do, creating one of the most intense working environments I have ever experienced. And there is something even more fascinating about this entire place. This structure was originally built back in 1946, making it one of the oldest and most important engineering projects on the Indus River. Located near Kalabagh, this is the first major control structure where the Indus River leaves the narrow mountain gorges and enters the plains of Pakistan. For decades, this barrage has been a lifeline for agriculture. By diverting water into a massive third canal system, it helped transform nearly 2 million acres of dry desert land into fertile farmland. The barrage itself contains 42 huge concrete gates, designed to safely pass enormous flood flows reaching up to 950,000 cusics. And years later, a modern hydropower station was added on the right side of the barrage, which you visit today. Using 8 horizontal pit type Kaplan turbine, this powerhouse generates around 96 megawatts of clean electricity. What makes this project special is that it produces power using only a very small water drop without building a giant reservoir or flooding large areas of land. It simply uses the natural flow and velocity of the river itself, and over time, the area upstream also become an important wetland ecosystem. Today, this region provides habitat for migratory birds traveling along the flyway and even support the endangered Indus River dolphin.
So the next time you see electricity coming from a canal power station, remember this hidden capsule beneath the water, a place where steel, pressure, vibration, torque, water, and engineering all come together. And honestly, would you be brave enough to stand inside this pit while 12,000 cubic feet of water rushing around you?